Good morning. My name is Gregor Dumpert, and today I'm presenting joint work with Robin Kramer and Armin Wittnim, which is about a novel paradigm, a novel approach in ultra-wideband localization and the associated estimators. Since this is a localization workshop, I think I can skip the general motivation for localization and ranging and look straight at the problem. And let's look here now at the conventional paradigm for wireless ranging. We have a node A, a node B, and a distance D between them. We have a channel measurement H, a channel impulse response, and want to estimate distance D. Usually this is done based on the received signal strength in H or the time of arrival. And this both has problems. The received signal strength fluctuates like hell from small scale fading antenna patterns. And the time of arrival has problems with non-line of sight bias and synchronization and multipath interference. So it's worthwhile to look at alternative approaches. This is the approach that we are going to consider during the entirety of this talk. So again, we have a pair of nodes A and B, a distance between them, or more generally, a relative position vector pointing from A to B. And now instead of looking at the channel between them, we are looking at the channels to a third node, which we call the observer node, one or more observer nodes, but here one is shown. And we compare now the ultra-wideband channels to this observer node. And this is quite similar to the fingerprinting idea. And many researchers have worked on that with machine learning. But the question arises, can we not do this with conventional signal processing and estimation theory, so more systematically without any training? And the answer is yes. And this is the topic of this talk. And the reason is that the changes, if the distance is small, are very systematic in the channel impulse responses. Let's have a look here now at this video. So we have here an observer, we have node A and node B. So they are very close together. There is a line of sight propagation path, a reflection from this wall here, and another reflection from this wall here. We have the channel impulse response between observer and A in black and between observer and B in blue. And you see now when B moves farther and farther away, the change here now is very systematic. So in all the three paths, line of sight and the two reflections. And we can utilize this systematic behavior to formulate estimators. And the idea is to extract the multipath components, associate them if the association knowledge is not given a priori, and then formulate an estimation rule based on the delays and maybe based on the multipath component directions. What would be the uses of such a scheme? So we could use the scheme to test for proximity between some mobile and some fixed beacon. And the charm here is that if this beacon with some low duty cycle transmits a pilot, then this channel is estimated. And this is the only thing that this beacon has to do. So it can be ultra low power, ultra low complexity. And this way we have something like a live updating fingerprint, and we can function in a time variant propagation environment. And what else is mentioned worthy here is that this approach works without a priori synchronization. Another nice application of this is a network with some fixed infrastructure like cellular base stations. And we can use those base stations now to compare the wideband channels to that between two mobiles and estimate the distance or the relative position here. And for example, for social distance monitoring, but you could also use this for the pairwise estimates required for cooperative localization. A very interesting property here is that this approach will work without knowledge of the observer locations. That means the observers can be mobiles themselves. So this approach works in all mobile networks without any fixed infrastructure, and you can do network localization with that. All right. And now let's look at the underlying properties of multipath geometry that make this possible. So we look here now at one multipath component represented in terms of its virtual source position here. And we have node A at position PA and node B at PB. We have the relative position vector between them. And of course, the distance is to a normal fit. And we have a certain multipath delay here and a delay here. And we have the speed of light c, and we have a direction vector EA and a direction vector EB. And now from this triangle, it is really trivial to state the following property, that this vector is the difference of this vector and this vector. But this is already very powerful for position estimation. So you see now, if we would actually have synchronous accurate estimate measurements here, then we can already determine the relative position vector from a single multipath component here without any use of environment information or observer location knowledge. So this is quite powerful already. But we will see that this rule alone leads to some problems. So we look at another property based on the delay difference. And we look at the following projection property here. So I let the math speak for itself. So we have here the delay difference given by this enum product. And with an assumption which is equivalent to a plane wave assumption, which means that here these directions are very similar. When this distance is small, this becomes even simpler. Another property that's also easy to derive from this triangle here is that the distance here between A and B inflicts bounds on the delay difference. So this will be very useful for distance estimation. And but before we look at this in detail, we have to discuss the system model. We have here typical multipath component parameters, delays, and the directions. A delay difference, true value, measured value, delay true value, measured value. We have a total of k multipath components, index k for the multipath components, and we have possibly multiple observers with index O. All right, what is the model here? Every multipath delay is modeled as its true value plus a measurement error plus an unknown synchronization offset. And what does that mean for the delay difference? We get a similar model, but now here again we have true value plus measurement error plus synchronization offset, but this now does not have an observer index, so that's quite interesting and important. This can be achieved when with some technical conditions are fulfilled. For example, when A and P send pilots in such a quick succession that a clock drift does not play a role at the observers, then this is given. And all right, let's move on to distance estimation now. We recall this property from earlier from the triangle. And when we now make some assumptions about the multipath directions, when we say they are random and we have a complicated propagation environment like indoor, so we say that the directions have uniform distributions and we use the plane wave assumption, then we can actually formulate the maximum likelihood estimate and base theorem, the minimum variance unbiased estimates jointly of distance and synchronization offset, given by these formulas here. So you see here the maximum delay difference minus the minimum delay difference over all multipath components. And this was already part of a previous conference paper. But now we are confronted with the problem that sometimes we don't know the multipath component association. So let's look at it here. When the distance between A and B gets very large, you see, then the order can change. So the second black peak is now associated with the third blue peak because the delays switched order. That means now it's very hard from instantaneous channel measurements to establish this multipath component association. So what can you do? You can either say, we just make the rather trivial choice by sorting. We associate first with first, second with second, third with third, and then just use this formula here, which can be suboptimal as we have seen here, because the sorted order must not be the true association. A more systematic approach would be to actually compute the maximum likelihood estimate for the appropriate likelihood function with unknown association. And this is what we did in this paper now. And you can see that the likelihood function is quite complicated with products over all observers and multipath components, but also a sum over all permutations between those multipath components. So you see this can escalate quickly. The details are given in the paper. So what are the performance implications? We make here now a performance comparison based on a typical indoor channel model with known association. We have like 1.1 meter error with 8 meters true distance. So this is quite good given the nature of the scheme. This is very promising, but without knowledge of the multipath component association, the errors are quite a bit larger. And you see that this very simple scheme of sorting is even better than the complicated maximum likelihood estimate. So there's no good reason at the moment to use this complicated estimate. But now that was distance estimation, but what about position estimation? I think we can do quite a lot better there. The idea here is that we will now use the direction information in the multipath components also, which we can do with antenna arrays. And we recall this property here from the triangle, and we will use this now to formulate an estimate of the relative position. So given are now the direction vectors of the multipath components, these are unit vectors, and measurements of the delays. What can we do with that? We can formulate the joint least squares estimate of the relative position vector and all the relevant clock offsets. And this can be obtained with some clever rearrangements of this and using the error model that we showed earlier. I will not go into detail here, but here you have a rule to compute this estimate in closed form. And let's look at the performance and then go back to the structure here to see what it's all about. The performance here is, first of all, extremely promising. You see that the position RMSE does not change with the true distance, so that's interesting. Also easy to see when you look closely at the formulas. And we have a couple of centimeters error even at large distances. So can this be true? The crux is that this estimator relies quite heavily on very precise direction information. So what happens when we have some errors in our MPC direction measurements? You see that the accuracy breaks down quite quickly. So with just 1 or 2 degrees of error here, the error position error just escalates. And the reason are these differences here between the MPC directions, and this is numerically very delicate. So, and can we do better? You maybe recall we looked at another property too, at this projection property. Maybe this can help. So this projection property restated here, or in terms of the plane wave assumption, might become simpler, allows us to formulate a different estimate, that is the least squares estimate based on such observations in terms of the delay differences. And the estimate is, the formulation is as follows. We can compute an estimate of the relative position vector jointly with the synchronization offset with this typical linear least squares form here and these matrices here. So another closed form estimator. And what is the performance of this delay difference based scheme now? We compare it to the previous one. You see here the blue one, the delay difference case is a little bit worse than the red one, so like twice the position error, but still it's very, very good. So it's like 5 centimeter error at even at large distances. But the great advantage of this scheme now is that it's much, much more robust against inaccurate direction measurements. So you see here that the position error increases with the direction measurement error standard deviation quite slowly. So it can handle even 15 degrees of error in the direction measurements. A last point that we want to address is the merit of association knowledge between the multipath components for position estimation. And I just want to mention that the multipath component directions at A and those at B, they are a premium a premium approach to establishing the correct multipath component association. When you just match this spatial signature from A to the one in B, you can achieve this. And for this purpose, we propose this rule here, which is similar to other approaches in the literature. And the performance implications are that it works very well up to quite some large distance. And then, of course, at some point, it breaks down. And the details, of course, you can find in the paper. Now, let me summarize my talk now. So we presented novel estimators for the distance or the relative position between a pair of nodes. And the core idea is comparing the wideband channel impulse responses to observer nodes in terms of the multipath components. The key technological advantages here are that the estimators do not require the following things. And this is very important now. We do not require line of sight conditions. We do not require precise synchronization or knowledge about the observer location, so the observers can be mobiles. We do not require knowledge about the propagation environment. We do not require a time invariant environment, and we do not necessarily require static infrastructure. We saw that the estimators offer great opportunities to wireless localization, so those use cases in cooperative localization and proximity testing to a point of interest. We already gave a practical proof of concept in the full paper, but certainly still an open task is the integration into existing robust real-time localization algorithms, where this new aspect in ultra-wideband localization could be used to improve existing schemes.